Previously, I told you that time value of money calculations in Excel are basically inputting the 4 parameters you know to solve for a 5th one you want to know. The 3 that we will focus on in this lecture are those that solve for present value, PV, future value, FV, and payment, PMT. As a reminder, when you invoke a function in Excel, it will give you a prompt like the one shown here that lists the required and optional parameters. Required parameters always come first, with optional ones indicated within brackets. For these, Excel will impose default assumptions if you don't specify these explicitly. For example, for the PV function, you must specify the discount rate, number of periods, and the payment. But if you omit the future value, it will assume a future value of 0. The type parameter prompts you to input a value of 0 or 1, where 0 indicates that cash flows occur at the end of a period, 1 indicating that they occur at the beginning. If you don't specify anything here, it will assume end mode by default. As you can see, each of these functions require you to specify a discount rate and the number of periods in question. The remaining parameters then cycle through whether the payment, future value, and present value are required options. We'll begin by examining applications of the first 2 functions for present values and future values. When you are calculating a present value, this suggests that you are trying to discount future cash flows. In other words, bring all sorts of cash flows that will occur in the future to the present. Remember, $1 today is worth more than $1 tomorrow. Hence, the present discounted value of future cash flows will always be a number less than simply adding up the raw dollar values of those future cash flows. And as I mentioned before, there are a variety of applications in both financial and managerial accounting where you will apply this. We can contrast this with solving for the future value of a stream of cash flows. We want to see how money today will compound and grow in the future. And one obvious application of this is planning for retirement. Let's start with a hypothetical example. Suppose you're going to receive $10,000 in 5 years and the discount rate is 6% each year. We want to calculate the present value of this future amount. To do this, we'll be using the PV function. And as you know, to solve for the present value, we're going to need to input some parameters. And we'll do this by typing in values in cells C8 to C11, which we will then reference in a PV formula in cell C12. First, let's enter the discount rate, which in this example is 6% annually. We can type 0.06 in this cell. Alternatively, we could type a 6 with the percentage sign after it, and Excel is going to recognize these as the exact same number. Next, we need to input the number of periods. Since we're looking at 5 years in this problem, we'll type a 5. But before proceeding, it's important to consider whether the units we've expressed for both the discount rate and the number of periods match with the relevant unit of time in the problem, the frequency of discounting or compounding. In this case, there's no need to make adjustments in our calculations because everything has been kept in annual terms. We're going to receive that 10 grand in 5 years and we have an annual discount rate. Everything's good. Next, we have the payment. For this problem, we're only dealing with a single future cash flow amount. There are no regular payments, so we enter a 0 here. Now we enter the future value. This is the amount we're going to receive in the future, which is $10,000. So we type in $10,000. Finally, we'll calculate the present value using the PV function, equals PV open parenthesis. And then we'll make references to the discount rate, comma, number of periods, payment, future value. And in this class, we're always going to do these at the end of the period. All cash flows will occur at the end of the period. That'll keep your life simple. So we'll type a 0 here, close our parenthesis, and hit enter. Let's interpret this. Our answer means that the present value of receiving $10,000 in 5 years, discounted at a rate of 6% per year, is $7,472. In other words, $10,000 in 5 years is really worth $7,500 today when we account for the time value of money. Let's try this again for our next problem, which deals with capital budgeting. It's always important to read these questions carefully. A company is considering investing in a new project to expand its operations. The project is expected to generate cash inflows of $400,000 at the end of each year for the next 5 years. The company's required rate of return, or discount rate, is 8%. Calculate the present value of the future cash inflows. Let's set this up again. You will see the discount rate expressed with a variety of terms in the future. It could be the market rate, an incremental borrowing rate. In this case, the relevant discount rate was the company's required annual rate of return of 8%. The project is planned to generate these cash flows for 5 years, so I'll type that in. Now, I've already spoiled this by including this information off to the side, but once again, there's no need for adjustments because these are annual cash flows, and if the relevant time unit is a year, then we can express the discount rate as an annual one. The number of periods we can just leave in terms of years. Next, payment. In this example, we do have a payment. At first, this might sound counterintuitive. We're not paying anybody. We're the ones receiving these cash inflows. But just remember, with time value of money, payment refers to equal recurring cash flows. We're going to get these $400,000 cash flows every year. So our payment is $400,000. Lastly, future value. Nothing was mentioned about any terminal cash flow occurring at the end of this project's life, so we can enter a future value of 0. Let's set up our present value formula then, equals PV. We've got our rate, number of periods, payment, future value. We've got roughly $1.6 million. Notice, this is smaller than just adding up $400,000 5 times. Let's show that. That would have been $2 million. But remember, the further into the future that we receive these cash flows, the less they are worth. So collectively, as discounted to the present, they really only amount to $1.6 million. And why do we care about this information? Because it informs us as to how much we should be willing to expend today on this project. If it's only going to cost $1 million, that's great. We'll give this project the green light. But if someone tried to convince you that you should spend $1.8 million on it, for example, they might point to this $2 million number and say it's worth it. But since you know your time value of money, you could do this calculation and say, really, those future cash flows are only worth the $1.6 million figure. Let's try a harder one. A company is planning to lease office space in a building for 7 years. The monthly lease payment is $6,000 and payments are made at the end of each month. The company's incremental borrowing cost, or the annual discount rate, is 4%. So what is the present value of these monthly payments? We can identify the rate pretty quickly, 4%. And the number of years in question, 7. But this time, these annual numbers do not match the relevant unit of time. We are making these payments monthly, so the discounting also has to reflect a monthly interval. When we do our PV calculation later, we'll need to make adjustments accordingly. We'll input a payment of $6,000 and a future value of 0. We only have the recurring cash flows of $6,000. And now let's set up our PV formula. First, we specify the rate. But remember, this discount rate was originally expressed in annual terms. So if I want this to be a monthly rate, I need to divide it with this slash by 12. Next, for the number of periods, we know it's going to be a 7-year lease. But in terms of months, this is going to be 7 times 12. And this is going to be a common pattern you're going to see. If you have an annual rate and number of years, you need to divide the rate by 12 and multiply the number of periods by 12 to get the right answer. We'll reference our payment, our future value, indicate that these occur at the end of the period. And once again, let's calculate the raw dollar amount of the cash outflows associated with this lease. $6,000 at the end of each month for 7 years, so multiply that by 7 and 12. So instead of putting $504,000 as a liability on the balance sheet, we'll express this as only $440,000. Let's do our last present value example. This one's the most challenging and it's going to deal with bonds. Essentially, bonds are just a huge loan that has been chopped into many little pieces that debt investors can purchase. The issuing company will make periodic payments, usually twice a year, and then pay back a stated face value at the end of the bond's term. Let's read the problem carefully. A company is going to issue a series of 30-year bonds. The annual market interest rate for bonds of similar size and risk is 7%. The bond will issue semi-annual payments to bondholders of $800,000 on June 30th and December 31st of each year. At the end of 30 years, the company will pay back the entire face value of the bond, equal to $50 million. Solve for the price, which is technically the present value, of this bond. So this one does start to get tricky. We have a discount rate of 7%, and the bonds are going to last for 30 years. But the unit of time is neither months nor years. These cash flows are going to occur twice a year. So later on, we're going to need to divide the annual discount rate by 2 to state it in semi-annual terms. And the number of periods won't be 30, they're going to be 60 payments for this bond. Need to multiply the years by 2. The size of the payments, $800,000. And in this example, we have both a payment and a future value. At the end of those 30 years, the company will also have to pay back $50 million to all of its bondholders. So with all of these inputs, we can solve for the price or present value of the bond. We'll take the rate, divide it by 2. Take the number of periods and multiply it by 2. Here's our payment, future value, and we get roughly $26 million. This means that collectively, debt investors would spend about $26 million to purchase this series of bonds, and this would also be that same amount of capital the company is able to raise by selling them. Now let's switch gears and do a couple of problems dealing with future values. These are less common in accounting, but I still want you to be familiar with the function. You decide to contribute $5,000 annually to a retirement fund. The fund is expected to earn an annual return of 7%. You plan to make these contributions at the end of each year for the next 20 years. So what will be the future value of your retirement fund after 20 years? Let's see how quickly we can zip through this. We got an annual rate of 7%. Number of periods, well, we're going to deal with 20 years. Let's check our unit of time. We are making these contributions at the annual level. So we can leave our rate as an annual rate of 7% and leave our number of periods in terms of years. The payment is going to be these $5,000 contributions each year. There's no present value here. We're starting from scratch. So it's a 0. This time we'll do equals FV, future value, specifying the rate, number of periods, payment, present value, all of these occurring at the end of the period. Well, that looks pretty good, $204,000. If we multiply $5,000 by 20, that only comes to $100,000. So we are more than doubling the raw dollar amount that we're putting in by accruing this compound interest. Let's try this last one. Suppose your retirement account has a current balance of $25,000. That's what we're starting with. You intend to contribute $200 to this fund at the end of each month for the next 15 years. If you anticipate an annual return of 6%, compounded monthly of course, what will be the future value of your retirement after 15 years? Okay, our rate is going to be 6%. That's our expected ROI. Number of periods, well, it's 15 years, but we got to go back and say this is being compounded on a monthly basis. We will have to make adjustments in our calculation. Our payment's going to be $200 each month, but we're starting with the present value of $25,000. That's what's already in there. Lastly, we calculate the future value by inputting the rate, but dividing it by 12, indicating that we've got 15 years, but there's 12 months in a year. Here's our payment and the present value of our current balance. And this gives us about $120,000. Maybe not enough to retire on right now, but we still have plenty of career left. 15 years, that's a good healthy start there. So I hope this has been some good exposure and practice with both the PV and FV functions in Excel.